Nutrient Cycles Part 2 examines the hydrological cycle, the cycling of water on Earth. The significant ideas are: the hydrological cycle is a system of water flows and storages that may be disrupted by human activity. Ecosystems are linked together by energy and matter flows. The sun's energy drives these flows, and humans are impacting the flows of energy and matter both locally and globally. Here's an image you've seen before. The Earth as a closed system, light, high-quality energy enters the system, is transformed into chemical energy by photosynthesis, flows through the system as chemical energy, as the energy moves through the food webs, and then leaves the system in a more disordered form known as heat. The biogeochemical cycles, the chemical elements and compounds cycle within the system among the living organisms and their physical environment. Here are the relevant IB syllabus statements for Nutrient Cycling Part 2. Describe the processes involving the transfer and transformation of water as it cycles within an ecosystem within the Earth's system. Construct and analyze flow diagrams of the water cycle. Here is a simplified diagram of the water cycle. You can see the transformations in blue and the transfers in red. Be careful here because you have to be careful with precipitation. Precipitation, rainfall, is actually a transfer, not a transformation. But precipitation has been preceded by condensation. Condensation is a transformation. We can see the magnitude of the flows as a function of their width. Remember that groundwater recharge is slow. Groundwater is renewable, but the inputs are slow, so groundwater must be managed carefully. Surface water, seen here, is a renewable resource. Here are two specific IB syllabus statements related to the water cycle. State that solar radiation drives the hydrological cycle. State that fresh water makes up only a small fraction of the Earth's water storages. Here is another simplified image of the water cycle, showing the relative magnitudes of the flows. Given the size of the oceans all together on Earth, it should come as no surprise that evaporation and condensation precipitation over the ocean would be quite large relative to the same processes over land. In one more simplified image of the water cycle, you can see the magnitude of the flows as rates. Remember that these flows here and here represent condensation first, with precipitation following. Condensation is a transformation, a change of state, while precipitation is just a transfer, a change of location. This flow is runoff, rivers to ocean. This flow is the transfer of water vapor or gas and clouds as liquid from one location to another. This flow is known as advection. In this image, we can see a slightly more complicated view of the water cycle. I would like to bring your attention to evapotranspiration, the evaporation of water from the leaves of trees as the trees bring up water from the ground through their root system. Evapotranspiration is a transformation. As well, you can see water vapor transport by wind. Here, this is known as advection, wind-blown movement. This would be a transfer of water vapor, gas, and cloud liquid. Runoff, seen here, is what you might see as stream, river, or flood condition. Runoff is a transfer, and without the impact of pollution, this transfer, runoff, would be clean water, ready to drink. Groundwater originates from two processes. First, infiltration, water on the ground surface enters the soil. And then secondly, percolation, seen here, where water seeps or filters through the ground without any definite channel. Now, keep in mind that that is how groundwater is recharged. Now also we have evaporation. This is a transformation, liquid to gas, and then condensation, also a transformation, water vapor, gas to liquid, then precipitation, a transfer. Here are the flows in the hydrological cycle labeled T1, T2 for transfers and transformations respectively. The T1, T2 designation is my notation, not that of the IB. The IB expects you to know which flows are transfers and which are transformations. They want you to know evaporation, evapotranspiration, condensation, which is gas to liquid, sublimation, solid to gas, advection, which is wind-blown movement, precipitation, a transfer, melting, freezing, surface runoff, infiltration, water entering the soil, and then percolation, moving through the soil without a definite channel. As well, you need to be aware of ocean currents, nothing more than a transfer. I'd like you to use this image to locate all of the flows of the hydrological cycle that I've mentioned previously. This image includes sublimation, which is a transformation of solid water directly to gas, ice to vapor. This image does not show advection well, which is the wind-blown transfer of atmospheric water vapor. Here are the storages in the hydrological cycle. The units for storages in the water cycle would be mass or volume units, no rates. I'll let you study this slide. Use this diagram to locate all of the storages of the hydrological cycle mentioned in the previous slide. The storages are noted in white color. Organisms are a storage of water. Ocean is a storage. Lakes, rivers, land or surface water. Groundwater, ice caps and glaciers, and atmosphere. And don't forget the fundamental difference between storages and flows, which are the respective measurements are different. Storages are not rates. Here is our last image of the water cycle. It shows both infiltration and percolation and advection as three transfers of higher detail of which you need to gain control. And here is runoff, streams and rivers, perfectly clean water without the impact of pollution. Keep this in mind. Water that precipitates high in the mountains to become runoff is perfectly clean water, ready to drink. Unfortunately, as water runs downhill into our cities, we change the quality of runoff. Ocean currents are related to the water cycle, though the currents flow within a single storage, within the ocean storage. Ocean currents move heat from warm equatorial regions to the poles. The ocean circulation systems are driven by differences in temperature and salinity, both of which influence water density. It is the difference in water density that drives the movement of the currents, serving to distribute heat and influencing local climate. The ocean conveyor belt is large-scale movement of ocean water as currents that serve to distribute heat from tropical regions to polar regions. You can see how water moves along the surface, then sinks due to density differences, then moves at depth only to resurface due to density differences. The flow of water within the ocean, known as ocean current, is driven by differences in temperature and salinity, both of which influence density. As you can see in this image, the ocean conveyor belt is referred to as a thermohaline circulation. Temperature, salinity, circulation. This is a diagram displaying mean surface temperature values as lines of a single temperature known as isotherms. These isotherms are for January. I'm showing you this diagram to illustrate the importance of ocean currents in distributing heat. If you follow a single line, say 5 degrees C, you're following a single temperature across the globe. Locations north are colder than 5 degrees, and locations south of that line are warmer than 5 degrees C. Keep this in mind. Let's start by looking at this image from a distance just to see the overall temperature pattern. Over land, notice that the isotherms dip to lower latitudes, indicating colder temperatures at relatively low latitudes in January. Over water in January, Isotherms push into higher latitudes, indicating warm water temperatures at relatively higher latitudes. In January, at a given latitude, land is colder than ocean. Land is colder than ocean. This is because oceans are moving heat. But let's look closely to see the real power of ocean currents for distributing heat. Let's follow this 5-degree isotherm, 5 degrees C, 45 degrees Fahrenheit, from land over North America into the North Atlantic. Remember, all the isotherms south of this 5-degree line are warmer, and all the isotherms north of this 5-degree line are colder. What we see when we follow the 5-degree isotherm is that it extends far to the north. Warm water extends far to the north to higher latitudes where you would expect the temperature to be less. These warm waters are pushing north. This is the North Atlantic Drift, or the Gulf Stream, that brings warm water from equatorial regions to north latitudes. The United Kingdom and the western coast of Norway are dramatically warmed by this current taking water from the equator to the north. Similarly, the western coast of South America is cooled by the Humboldt Current, bringing cold water from the South Pole to the equator. The coast of Chile and Peru are cooled by the cold water moving north. Differences in water density drive ocean circulation. Water density is influenced by both temperature and salinity. Again, notice how this relatively mild -1 degree C temperature extends nearly to the Arctic Circle. The western coast of Europe, particularly Scandinavia, is significantly warmed by ocean currents carrying heat from lower latitudes. Here are 2 IB syllabus statements of relevance. Describe the impact of human activities on surface runoff and infiltration, including agriculture, deforestation, and urbanization. Discuss human impact on the hydrological cycle. Here are the impacts. Humans are changing rates of extraction, thus there's been a reduction in water storages, reduction of river flow, and groundwater. Humans are redistributing water, moving surface water from one location to another using canals. As well, humans are slowing surface flow behind dams. Humans are changing the rates of evaporation and infiltration and runoff through agricultural practices and deforestation. And humans are changing the quality of runoff through pollution. Urbanization and increasing population numbers are putting pressure on water resources, exacerbating, making worse all of the ways in which people interact with water. Agriculture has an impact on surface runoff and infiltration. Irrigation extracts water from rivers and spreads it on the land. Now, as I present images of human impact on the water cycle, I want you to be thinking, what's the impact? Is it extraction, a reduction of storage? Is it a redistribution, a canal or dam? Is it a change in the rate of evaporation, infiltration, or runoff? Or is it a change in the quality of the runoff? Is it pollution? Or is it all of the above? Irrigation canals divert water from the river's channel and redistribute the water to locations that need more water. Now be thinking, what is the impact? Is it increasing rates of extraction with a reduction of storage? Yes, that would be true here. Is it a redistribution of water in canals? Yes. Is it influencing the rate of evaporation? It might be if there's evaporation from these canals. Is it influencing the quality of the runoff? It depends what's running off these fields into this water. So much water is extracted from rivers that some rivers no longer or rarely flow to the ocean. This is a photograph of the Colorado River in Mexico as it approaches its outlet with the ocean. There's not much left. Irrigation flooding increases the evaporation of water into the atmosphere and increases the infiltration of water into the soil. Agriculture. Surface and groundwater irrigation dramatically redistributes water. Surface water and groundwater storages are highly reduced as a result of irrigation. Irrigation dramatically redistributes water. Groundwater storages are highly reduced as a result of irrigation. And a lot of what once was groundwater now evaporates into the atmosphere. Urbanization has increased the demand for water, increasing the amount of water extracted and diverted from the original channels. Urbanization and increasing population size have increased the need for irrigation. Large populations need food, and the need for food has increased the demand for water. Dams, as you can see here, have been built to provide water. But dams have changed the course of rivers. Large volumes of water are now held behind dams. Now I want you to be thinking, what's the impact? Is it increasing rates of extraction with a reduction of the storage? Is it a redistribution of water in canals, in dams? Is it influencing rates of evaporation or infiltration, runoff? Is it influencing the quality of runoff, pollution? Deforestation reduces the infiltration of water into the soil because the water that falls on the deforested land runs off the land quickly. Deforestation reduces evapotranspiration, less water released to the atmosphere by the land. Less water in the atmosphere means less precipitation. Now be thinking, what's the impact of deforestation? Is it increasing rate of extraction with a reduction of the storage? Is it a redistribution of water in canals or dams? Is it influencing the rate of evaporation or infiltration and runoff? Or is it influencing the quality of runoff, as in pollution? Deforestation reduces the infiltration of water into the soil. Water runs off the land quickly, and the erosion of soil increases. In this photo on the left, the burned forest results in rapid water runoff into the gully, and this increases the rate at which the gully is eroded. Notice how water erosion has gouged the gully. Increased rates of runoff muddies rivers below, resulting in the increased flow of sediment to where rivers meet oceans, seen here on the right. Deforestation decreases natural infiltration and increases runoff. Soil integrity weakens. Landslides are the result. Deforestation alters the quality of water runoff. Trees hold soil. Thus, deforestation results in soil loss, an acceleration of erosion, as can be seen in this river. In Thailand, deforestation has accompanied an increase in population size and urbanization. The political boundary of Thailand is nearly discernible as deforestation. Unlike Laos or Myanmar or Cambodia, Thailand's deforestation defines its political boundary. The world's population is 7.2 billion and growing. 51% of the world's population is now living in a city, and the percentage is growing. Both population growth and urbanization are putting pressure on water resources, increasing the demand for fresh water. Urbanization alters runoff, as you can see in the slide. Urbanization alters infiltration of water into the ground. Urbanization prevents water from naturally infiltrating and percolating to become groundwater. Flooding can result. Urbanization decreases infiltration and increases runoff. Flooding increases. Urbanization decreases infiltration and increases runoff. Urban flooding increases. Pollution alters the quality of surface runoff. People use the flow of rivers as a means to get rid of waste from their immediate environment. As a result, most surface water is not drinkable. With urbanization comes sewage. Pollution, such as sewage, alters the quality of runoff. People use the flow of rivers as a means to get rid of waste from their immediate environment. As a result, most surface water is not drinkable. Over the last 20 slides or so, I have presented these two IB syllabus statements. I have suggested that human activities are having the following impact on the hydrological cycle. We are changing rates of extraction and reducing storage. We are redistributing water with canals and dams. We are changing rates of evaporation, infiltration, and runoff, and we are changing the quality of runoff. Urbanization and increasing population numbers are putting pressure on water resources, making worse all of the ways in which people interact with water. Let's bring this movie to a close with a bit of review of water on Earth. Remember, the characteristics of the Earth's biomes are determined mostly by the presence or absence of water, as well as a prevailing temperature, as well as available light. Remember that rainfall varies by latitude. Equatorial regions receive the most rainfall, and polar regions receive the least on average. Regions that are 30 degrees north or 30 degrees south of the equator also receive very little rainfall. The tricellular model of air circulation explains the distribution of precipitation and temperature. If you're not sure about the tricellular model of air circulation as an influence on the distribution of biomes, please review Ecosystems 2, Part 6. This diagram displays evaporation versus precipitation by latitude. Where evaporation is greater than precipitation, values are positive, and where precipitation is greater than evaporation, values are negative. You can see that when evaporation is greater than precipitation, again, positive, colored yellow, we would have deserts. In regions where precipitation is greater than evaporation, say purple in this diagram, we would have rainforests. While precipitation is low in polar regions, so is evaporation due to the cold temperatures. Thus, polar regions are negative slightly. There is slightly more precipitation than evaporation. But 30 degrees north or south of the equator are deserts, where evaporation is significantly more than precipitation. Again, your understanding of the tricellular model of air circulation to understand biome distribution is very important here. Review Ecosystem 2, Part 6. And that brings us to the end of IBESS Nutrient Cycles, Part 2.